let's get started. Good morning and good afternoon, everyone. Welcome to today's Adams webinar titled Adams Matlab Cosimulation for Vehicle ABS Systems. My name is Yijun Fan. I'm the Product Marketing Manager for Adams and EV5 at MSC Software. Here's the agenda for today's session. To kickstart the presentation, and to those of you who are not necessarily very familiar with Adams Car, I'm going to have an overview of some of the vehicle dynamic events that's already available in Adams Car. After that, we will talk about how we can couple Adams Car with control software. And before we go to the live demo showing the ABS system evaluation, we will go through two case studies just to have an idea of how some of the existing customers are leveraging this technology to help with their vehicle development process. And at the end of today's webinar, there will be about 10 minutes Q&A session. So if you have any questions regarding today's presentation on Cosimulation or Adams itself, please type the question down in the Q&A window. We will try to either have them answered during the session or we will follow up with you after the event. Okay. First, Adams Car. As we all know, Adams Car is capable of dealing with a wide variety of different vehicle applications. Probably it's best known for its capabilities in handling and ride analysis area. But Adams Car also deals with safety. Now, when we talk about safety here, we don't necessarily mean the front crash or some of the explicit nonlinear analysis out there, but more we're talking about how to perform a vehicle analysis so we can study under which conditions the vehicle is going to lose control, spin out, or even roll over. And sometimes you can couple Adams with other control softwares to study things like the ABS system or the electronic stability controls. Of course, in the durability area, Adams is well known for its high accuracy in predicting the load history on different components. And then those information will be exported to an FEA software or fatigue software to further study the durability or the stress and strain of certain components in a vehicle. So as well as those full vehicle events that we talked about here, Adams Car also serves as a very robust input into some of the subsystems, such as the powertrain or the drivetrain. Those detailed models can provide a very accurate prediction and adds fidelity to the full vehicle simulation. And conversely, the full vehicle simulation can be served as a boundary condition when you are analyzing those subsystems or components. Here is a small subset of all the automotive customers in the world that are using Adams in their R&D processes. And it's indeed worth mentioning that the top 20 car manufacturers by volume globally all use Adams products. Now let's take a look at some of the more detailed applications for Adams Car. Adams Car is programmed with a variety of standard suspension and steering events. And here you see on the screen is an opposite wheel travel, and of course, we support component flexibility, whether it's linear flexibility or nonlinear flexibility. Adams Car is also commonly used to study the vehicle handling analysis. In the animation you see here on the bottom of the screen, it shows a military vehicle goes through a double lane change. So first, it will enter a set of obstacles in a preset speed. Then it will undergo a deviant movement to the left and then to the right in a predefined distance. As the vehicle goes through all the obstacles, you can see on the screen the corresponding forces and moments at the center of all wheels. This is due to the sudden lateral movement or displacement of the vehicle. Adams Car comes with a set of open loop steering events. By open loop, we mean there's no feedback in the system, which means the input is not going to be affected by the output of the vehicle. Also, we support a list of cornering events in both steady-state maneuvers, like the constant radius cornering you see in the animation here, and also some of the transient effect, like the power-off cornering or braking turn. Other predefined events include the straight-line events, such as acceleration, braking, braking on split mill surfaces, and also the road stability events, including embankment, corkscrew ramp, and sandbag. In cases where when your required simulation event is not in any of the predefined event library, in case you want to create your own event for your specific vehicle tests, you can certainly do that. In this example, I was asked by my managers to create a scenario where it has a very strong Christmas or holiday flavor. And in one of the scenarios, the vehicle needs to be parked into a garage. And this is not defined by any of the pre-existing library that we can find in Adam's car. And that's when I used the event builder to define the trajectory and also the speed of the vehicle at each point of that trajectory. I used the DCD file to set those events. But you can, besides the open loop events, you can also define the closed loop events using the event builder. And by closed loop event, there is a closed loop controller within Adam's car, and it's called the SmartDriver. With the closed loop controller, there is feedback, which means the input can be influenced by the output. With the SmartDriver, you can drive a vehicle at a predefined path with the vehicle's limits, acceleration that's automatically computed for any specific road. Or you can use your user-defined proportion of the vehicle's maximum capacity, like the acceleration or steering. So in order to connect your Adams model to a 1D diagram model like EZ5, Matlab, or any control software that supports the FMI standard, you can use Adams controls to link those two disciplines together and study the interaction between the controls, electronics, hydraulics, and your mechanical systems like a full vehicle. And the product here we use is called the Adams control, which we will illustrate later in the demonstration. Now here's an example of, from Ford of how they leveraged the Cosimulation technology to optimize their trade-off between the fuel economy and the NVH. So the challenge here is that a lugging behavior was observed in some of the vehicles. Lugging is a condition in which the vehicle is very commonly when a vehicle is in high gear and low engine speed, it will cause a high level of low frequency input, which can be translated into the excessive vibration in the seat track or in a steering system that the passenger can experience, which is not ideal. In order to reduce or minimize that lugging effect, there's a torque converter. So the torque converter is basically equipment that was used to transmit the torque between the engine and the transmission. There's a slip RPM that you can set in the torque converter. And the higher the slip RPM on that torque converter, the better the NVH performance. And the lower, and you can also lock up that converter, which means there's a 0 RPM slip on that converter, which will translate into 100% transmission efficiency between the engine and the transmission. But that will oftentimes cause a lot of NVH problems like the lugging. So as a result, you need to find a balance between the fuel economy and your NVH performance by tuning the slip RPM on your torque converter. And in this example, there is a high-fidelity torque converter model in the AME simulation software, and there's also a full vehicle model that was simulated using Adams driveline. As a result, for the combination of both software, the AME sim and Adams connected with FMI standard, the engineers were able to study different values of the torsional vibration with a range of desired slip RPM across a broad range of engine RPM, as you see on this picture shown here. For every slip RPM, we study the vehicle performance across a broad range of different engine RPM. And each line here with different colors representing the vehicle performance at each certain slip RPM. And as we see, the lower the slip RPM of the torque converter, the worse the NVH performance. But at the same time, we know that if we tune the slip RPM at a very high level, it will compromise the engine's fuel efficiency. And there's also a line that dedicates the lugging target, which means across a broad range of different engine RPMs, the NVH performance, the torsional vibration has to keep below that lugging target. And we see there are three different results that can meet this NVH requirement, which is when the slip RPM is equal to 40, 50, and 60. As we also know that the higher the slip RPM of the torque converter, the worse the fuel efficiency of the vehicle. And that's why we are choosing the optimum value, which meets the lugging requirement, but is also the most fuel efficient option, which is when the torque converter is slipping at an RPM of 40. And that's how we are using the combination of a high-fidelity torque converter model in a control software and a full vehicle model in Adams to evaluate at which scenario that we will have a best trade-off between the fuel economy and the NVH. Next example is from Meritor. The whole purpose behind this project is to optimize their control algorithm in order to cope with a new change in the federal regulation that requires a 30% reduction in stopping distances for heavy trucks. As a result of co-simulating between Adams and their in-house control algorithms, they were able to evaluate and optimize their control logic, and allowing the vehicle to reduce the stopping distance for exceeding targets by 28%. But they didn't change any current disc braking system, so the hardware remains the same. The only thing that has been changed is the control logic. And by connecting the mechanical system and their control software effectively, they were able to come up with an optimized control system which can help them reach the target while maintaining their existing lighter brake design. Okay, now let's take a look at a demonstration that will show you the entire workflow of connecting Adams with the control software like Matlab Simulink. So here is a full vehicle model that we have set up in the Adams car environment. There's one thing that's specific to this model is the brake system. So here is the brake system that I opened it up in the template builder. As you can see, we have defined a set of state variables to be used as the input and output between Adams and Matlab. The entire logic between this co-simulation for the ABS control system can be seen on this slide. In this scenario, we're using the fastest wheel speed to be defined as the vehicle speed. And a locked-up wheel is going to be slower than the other side of the wheel. And we're calculating in a slip value in the Adams Matlab controller, which is basically this equation. So the fastest wheel speed minus the current wheel speed divided by the fastest wheel speed. And when this slip ratio is larger than a threshold, we say we need to release the brake to maintain the steering of the vehicle. And if the slip value is smaller than the ABS threshold, here we define the threshold to be 5%, the brake will continue to be taken into effect. And that's the basic logic behind this co-simulation or communication between Adams and Matlab. And that's why we're defining a set of state variables. First is a set of ABS state variables called the ABS input. The default value is set to be 1, which means if the Matlab does not ask Adams to release the brake, it will continue to apply a brake torque to the vehicle. And that ABS input is taken into account within this brake torque variable. As you see, we have a parameter defined here, which is basically the value or the state variable that we defined earlier with the ABS input. So if Matlab tells Adams to release the brake, it will give a value of 0 to this state variable. This will be changed to 0, which means there's not going to be any brake torque on that specific brake at the moment. There's also 4 state variables that are used as the output from Adams into Matlab, which can be used by Matlab to calculate whether or not the wheel is locked up or whether or not the slip value is larger or smaller than the ABS threshold. Those are the brake velocity at each wheel. Now with that defined, let's go ahead and continue with our co-simulation process. In the beginning of the simulation, I'm going to perform a brake event. So I will go to the full vehicle analysis, straight line events, and braking. Here, let me set the output prefix to be the name ABS. Let's have 4 seconds and 400 steps. Since the purpose of this simulation is to output the Adams model, so I will perform a files-only simulation here. For the road data, we will use a split mu road file that we have defined previously. Now let's take a look at this road file. You can see that the friction coefficient is different from the left side of the road to the right side of the road. And that's why it's going to cause a slip effect during the simulation. Let's use this road as our road data file. Choose the locked wheel. Start time 1. Final brake 100 and 1.5. Here position 4. Uncheck the quasi-static. Now we see that right now there are only 2 files, which is basically the controller, the Matlab controller for our ABS system. Now I'm going to perform this file-only simulation. And next, what I'm going to do is to export the plant using the plugin of Adams Controls. As we mentioned before, we have a plugin called Adams Controls that can enable the connection between Adams and the control software. Before you are using Adams Controls, you want to make sure the plugin is loaded in the plugin manager. Now let's go to the plant export. All right. Here we will be defining what are the input and output parameters from between Adams and Matlab Simulink. And we will use a set of predefined inputs and outputs that we introduced earlier. So Adams will output the speed of each wheel to Matlab Simulink, and then Matlab Simulink will decide whether or not to release the brake on the vehicle. In the target software, we will change that to Matlab. And then let me just let's make sure that we are choosing the correct folder as our default folder. And we can close our template builder here. Besides the EZ5 and Matlab, if you're using other control softwares like AME Sim or Simulation X, you can choose our FMU standard as the connection between Atoms and other control systems. But here for Matlab, there's a default connection, so we will just choose the Matlab for now. And when we click OK, we will output an M file, which can be used to set up the connection between, the M file will basically define what is the input and output between the Atoms and Matlab. All right, with that created, let's go to our Matlab Simulink. And in the Matlab, you can see that we are setting the working directory to be the same as our Atoms car working directory. So the first step we want to do is to load in the M file that we just created, which defines the input and output between Atoms and Matlab. The next step is to loading the controller. Now you can directly load in the controller, but we use another M file called the ABS setup, which also defines the threshold of the brake system. And if you open up this controller, you will actually see that it's nothing more than just definition of the threshold and also the control algorithms for the ABS controller, as you see here. And the third step, what we want to do is to load in the Atoms system model. And we will type in Atoms this here. And this will be the Atoms model that we just generated. What we want to do is to copy this Atoms model into the controller and replace the previous old block with this new Atoms model. And at this point, we can start initiate the cosimulation. And sometimes you need to do some fine-tuning. For example, if you are connecting a 32-bit of Matlab with a 64-bit of Atoms software, you need to use the TCP/IP connection instead of the pipe connection. Those are the settings you can change in the Matlab Simulink. Now the simulation, the co-simulation is initiated, and Atoms and Matlab is talking to each other constantly to make sure that the vehicle is maintaining its stability without, spinning out. Okay, now the simulation is finished. And with the completed simulation, we are able to see there's going to be a result file generated within the control system. As you see here, this is the new results file that was generated by the system. And let's load in this result. This is created at 10:28. It was just created by this co-simulation. And the model is the one that we're going to choose, the converter ABS. Okay, now before we go to the post-processor, let's perform another standard event without the connection to Matlab. So let's perform the same event, same break event. So instead of the files only simulation mode, we're going to change it to interactive. And the output prefix is no ABS. The other parameters remain the same. Okay? Now we're going to run another vehicle simulation, just as a baseline to show you what the vehicle will, how the vehicle will perform without the ABS controller being connected to the Adams model. Okay, the simulation is completed. Now let's go to the post-processor. In this working directory, you can see we have a new results file generated called no ABS break. Okay, first, let's loading the animation with the Cosimulation results. And then let's loading the animation in the scenario where there's no ABS in the system. And as we know from experience that with if the ABS system is activated, it's going to take you a longer distance to put the vehicle to a stop, but you can keep maintaining your vehicle steering, you can keep maintaining the direction of your vehicle, and the steering is still going to be effective. But in the event when there is no ABS brake and the road is slippery, and slip ratio or the friction ratio between the left side of the road is different than the right side of the road, you will see the spinning effect of your vehicle. And let's play the animation now to do the comparison. And the upper one is the scenario where there is an ABS brake, and the lower one is the one without the ABS brake. And you see in the lower case, the vehicle spins out at some point during the simulation. And in the upper animation, you see that the vehicle remains control of the steering throughout the whole courses of braking events. And let's also take a look at the vehicle yaw rate. Let's compare both events, see if there's any differences between the two events on the yaw rate. We will use the body yaw rate as the parameter here for the plotting. So you can see the plot illustrates that the red curve represents the event with ABS, and the blue curve represents the yaw rate of the vehicle going through the event without the ABS brake. And it's pretty obvious that the one with the ABS brake, the yaw rate keeps to a minimum value, but the one without the ABS brake, the vehicle starts to spin during certain instant of the simulation event, and that makes sense to our common knowledge. So that is the entire workflow of connecting Adams with Matlab. This vehicle model and this ABS example is going to be available for public usage. So if you are interested in that, you can send me an email. I can send this model to you so you can play around with that. If you have both Matlab and Adams on your computer, you can play around with that by yourself. I can send you a copy of the model if you want to. All right, with that, we will go to the Q&A session.